So please start. Yeah, please start.
Okay, so thank you to Masashi very much for the invitation to speak. It's a great pleasure to be here. And I'm going to talk about a paper that appeared last September with my collaborators, Roland Bittleston, who's a postdoc in Perimeter Institute, Simon Herverline, who was my PhD student at the time and is now in Harvard, and Surya Raghavendran, who's a postdoc in Edinburgh. I think he's moving to Yale. Okay, so how do I go forward? Oh, wait, how do I go forward? Sorry. Just a second. Okay, so the talk's about the Kadomtsev-Piashvili equation, the KP equation. And this nonlinear PDE. And it's a famous PDE. It's an integral system which describes the evolution of the height of some shallow water waves moving on the surface of some water in time. It's a generalization of the even more famous KdV equation, which describes water propagating just in one spatial dimension, and if it reduces to the KdV equation in the case that there's no extra dimension, no extra dependence on that extra dimension. So as you can see from this equation, the KP equation is not rotationally invariant. It singles out this direction x, and physically that means that the waves can't just travel in any old direction on the surface of the water. They have to travel in some preferred direction, which we can think of as being towards the beach. And as I mentioned, it's a famous example of an integrable system. Now, my interest comes because there are lots of broad classification schemes for integral systems. We'd like to understand what it is, what special properties these integrable equations have, how we can tell whether an equation is integrable. And among many others, the ones that I'm particularly interested in are the idea that all integrable systems come from twistor space. This is an old idea going back to work of Richard Ward and earlier Penrose, carried on by many people, including Nigel Hitchin, Lionel Mason, and others, starting in the 1980s. And a much more recent idea, which was pioneered by Kevin Costello, Masito Yamazaki, and Edward Witten, on the idea that they all come from some sort of mixed topological holomorphic theory. I'll say much more about what they are in a minute. Now, until recently, these KP equations didn't really fit into either of these schemes. And our work was about trying to understand how to construct an example of both of these type of constructions, the twistor construction and mixed topological holomorphic theory, such that the KP equation did fit into these schemes. So before we jump into KP, let's just sort of warm up with some more well-known integral systems that do fit into these schemes. And in fact, actually, these two different schemes, the twistor approach and topological holomorphic approach, are very, very closely related. In particular, both of them try to describe an integral system by constructing a higher dimensional system that incorporates the spectral parameter into the geometry. So we have some higher dimensional theory that lives on some space together with the spectral parameter space. And altogether, this is equivalent to some lower dimensional integrable system. That happens in both the twistor approach and these topological holomorphic approaches. The simplest example of this is probably self-dual Yang-Mills theory on R4. And to set this up in twistor space, let's recall that the twistor space of R4 as a smooth manifold, it's just a six-dimensional manifold, which is just R4 cross S2. We'll think of S2 as being the space where the spectral parameter lives. But as usual, when we've got a spectral parameter, and as usual in twistor theory, we want to think of this space not as a smooth six-manifold, but as a complex threefold. And we can do this by taking a holomorphic coordinate lambda, so lambda alpha here are homogeneous coordinates on this S2 or CP1. And then we split R4 we think of R4 as C2. But the way we choose our holomorphic coordinates, which combination of our four real coordinates we're going to pair up to think of as holomorphic coordinates on C2, varies as we move around on the CP1. So we take this combination, mu, which is x contracted into lambda. So x here is a little 2x2 matrix encoding the four real coordinates of R4. And this linear combination is the combination of coordinates I'll think of as holomorphic coordinates on my C2. So in my diagram here, I've got a little picture of CP1 just drawn as a one-dimensional line. You should think of it as a complex line moving along the bottom. And above each point on CP1, I've got a copy of of R4 being thought of as C2, but these little axes rotating around are supposed to indicate that we think of it as C2 in different ways as we move around on the CP1. Now, on this six-dimensional space, on this complex threefold twistor space, we write down a holomorphic BF theory. So here, omega is just the natural holomorphic three form on this space, which under scaling of the homogeneous coordinates has got weight 4. So we just build it from the standard measure of weight 2 on CP1 together with the holomorphic 2 form built out of my holomorphic combination of coordinates. And then, since this soaks up all the holomorphic forms, what's left over, the Lagrangian, this BF Lagrangian, only points in anti-holomorphic directions on twistor space. And it includes a Lagrange multiplier field, which has got weight to soak up the homogeneity of this holomorphic 3 form I use. That's this weight minus 4 here, together with the 0-2 form part of a curvature of a partial connection. It's important to note that this theory in 6 dimensions doesn't involve any metric on the twistor space. It's purely obtained by wedging together these forms. So there's no metric. However, because these fields, as usual for a gauge theory, define modulo gauge redundancy, it might be that we want to introduce a metric in order to fix this gauge redundancy. But any such metric will only appear in gauge fixing terms. Now, that's important for understanding how this 6-dimensional theory can be equivalent to a theory in 4 dimensions, because, for example, we can choose to introduce a metric. We can choose to gauge fix by introducing a metric such that the volume of these CP1s is 0 or gets very, very small in our chosen metric. And in that case, normally you'd say that if I Kaluza-Klein reduce my higher dimensional theory, normally you'd say that you have an infinite tower of some sort of mode expansion on the compact space, and at low energies, you'd normally say that only the 0 mode survives. So normally you'd say in a typical theory, you'd say that at low energies, your theory reduces to 1 in lower dimensions when you Kaluza-Klein reduce. But here, because there's no metric on our twistor theory, we're kind of automatically in the far infrared limit. We're far down at low energies because we can choose the scale of this CP1 to be as small as we like. Whatever scale we choose it's all gauge redundant. And so up to gauge transformations, this holomorphic BF theory is going to reduce to some theory on R4. It's going to be exactly equivalent to a theory on R4. And without going through the details, the theory on R4 you get is, probably not too surprisingly given the structure of the Lagrangian we started with, just self-dual BF theory. So this field capital B, of course, is inherited from the little b up on twistor space, and it turns out to be self-dual if you go through the details of the reduction. And again, it just wedges against the curvature in 4 dimensions. So the field equations of this thing just impose that the self-dual part of F is 0, so these give us the anti-self-dual Yang-Mills equations. Okay, there are many other ways we can get anti-self-dual Yang-Mills. You might think that this sort of Lagrange multiplier type action is a little bit clunky. Of course, there are better ways or different ways of getting it, at least in terms of Yang's J and K matrix formulations, various other formulations. All of those can be fitted into this twistor paradigm as well, and this holomorphic field theory paradigm as well. I just wanted to go through this one as the simplest example of how to get it. So as I say, there are many further examples which come from allowing this top form, this 3-0 form, to not just be the one that we wrote down, which was just here, just the measure on CP1 together with the 2d mu's, but also allowing it to have some zeros or some poles, and maybe by imposing some sort of symmetry reduction. To get us a little bit closer to the topic of this talk, which is the KP theory, let's consider the example of monopoles in R3, which will be described using mini-twistors. So what's a mini-twistor? So mini-twistor space is the space of oriented geodesics in R3. And you can think of it just as the tangent bundle to S2, tangent bundle to CP1. So why is that? Well, let's imagine we're in R3 with some origin here. In order to specify an oriented geodesic, the first thing we'll do is just pick a direction that oriented geodesic is going to travel in. And that direction is labeled by a point on S2, a point on the unit sphere, if you like. And then having picked our direction, I then translate in a direction orthogonal to the sphere until I meet the actual geodesic that I want that points in the same direction as my initial direction. So in other words, I pick a point on the tangent space to the sphere at this point, corresponding to the direction. Now, this mini twistor space, how is it related to R3 more mathematically rather than just this geometric picture, more algebraically? Well, it fits into something called a double fibration. Sitting on top here, I've got a space that I'll call PS, or the projective spin bundle. And that's the space that's got coordinates x, which are just coordinates on R3. So alpha and beta here are two component indices, and x is a symmetric 2 by 2 matrix. So it's got three real components of R3 sitting inside it. And then again, I've got my homogeneous coordinates on the CP1, lambda alpha. And these two projections, P and Q, well, Q is the most obvious one. Of course, I just forget about the Riemann sphere. I just keep hold of my x's, forget about the Riemann sphere. And so the fiber of this projection is just an S2. On the other hand, to project down from this spin bundle to mini twistor space here, I project by contracting x on both indices with this lambda. Okay, so I construct a coordinate mu by contracting x on both indices with this lambda. And again, you can think that what I'm doing is I'm choosing a copy of the complex plane inside R3 to think of some holomorphic coordinates. But which bit of, which R2 inside R3 I'm choosing varies as I move around on the Riemann sphere. And it's this combination here that is the coordinate that I'm going to treat as my holomorphic coordinate on the Riemann on the complex plane, along with the Riemann sphere. Now, similar to self-Joule-Yang-Mills, we can just write a BF theory on this spin bundle, this space at the top of my fibration. But now it's going to be a mixed topological holomorphic thing. So again, I'm going to wedge it against a holomorphic 2 form. And this holomorphic 2 form is just the standard holomorphic 2 form on the cotangent bundle to the sphere. So that's the standard holomorphic 2 form on twistor space, pulled back by this left fibration. So the mu and lambda coordinates are coordinates down on my mini twistor space, and I just pull it back to the spin bundle and wedge it against BF. So this spin bundle altogether has got 5 real dimensions. And so since I've pulled back a 2 form, what's left must now be a 3 form. And this 3 form takes a standard form, but my fields, A and B, will have a component which I've called a vertical, which will point along this real fiber of the fibration of PS over mini twistor space. So it'll have a component that points along this fiber here. And it'll also have a pair of components that are 0-1 forms on the mini twistor space itself, downstairs. Okay, so I call these 0-1 tilde, where the tilde just reminds me that it's also got this additional component pointing along the fiber. Similarly for B. And we can think of these tilde 0p forms as just being those forms which wedge to 0 against the pullback of this holomorphic form. So, sorry, I got that wrong. They're the complement of the forms. So they're all forms modulo these guys. Okay, so just to say that again, these forms are built out of 3 ingredients. There's the anti-holomorphic forms on mini twistor space itself, so 0-1 forms on mini twistor space itself, pulled back to the spin bundle, together with this extra real form that points along the fibers of mini twistor space, of the spin bundle over mini twistor space. And likewise, this tilde derivative up here, the kinetic operator, again, it's the d bar operator together with the de Rham operator pointing along the fibers. Now, because of this sort of mixed structure, that it's got the de Rham operator along the fibers, but the d bar operator in directions along mini twistor space, this theory is so-called mixed topological holomorphic. It's topological along the fibers of this fibration, but it's holomorphic in directions corresponding to directions along the base. Now, suppose we gauge fix in the same way as we did for self-Joule-Yang-Mills. That is, I'm interested in the right-hand side of the fibration. This is the fibration of this spin bundle over R3, which is just S2 cross R3. And suppose I gauge fix by picking a metric that sends the volume of those fibers to 0. Then again, you can easily reduce this action, and you find a sort of BF-type action downstairs, but which now imposes the Bogomolny equation. Again, the B field here descends from B, and the A field descends to give both the curvature and this derivative of a scalar, of a covariant scalar, again, depending on whether you're looking at what started out life as the vertical components of A or the mini twistor components of A. So this is what you get down on R3. And it's just a Lagrange multiplier describing the Bogomolny equations for monopoles. Alternatively, if we work in a different gauge, instead of introducing a metric, I could alternatively choose to impose the gauge where the vertical component of this gauge field is 0. Then just expanding out the different components of this action, what you find is this. So if B doesn't point along the vertical direction, then it must be this curvature that points along the vertical direction. And the only thing that can do it is the derivative, since we set the vertical component of the gauge field to 0. And so integrating out this B bar just tells me that A bar, the remaining components of the gauge field, are independent of this fiber direction. They're constant along the fiber. And therefore, the remaining components have been pulled back from something that lived on mini twistor space itself. And finally, the equations of motion from varying the vertical component of B tell me that those remaining components of A defined a holomorphic bundle rather than just a complex bundle, a holomorphic bundle on the mini twistor space. And again, that's Hitchin's description of monopoles. So we're relating the Bogomolny equations to Hitchin's description of monopoles via holomorphic bundles on the mini twistor space, all through this mixed topological holomorphic action using various gauges to see the equivalence. Okay, so now let's move to the actual topic, which is mini twistors and KP. Now, although the KP equation itself, the full KP equation, hasn't really fit into twistor space before, it's got a dispersionless limit. That's where I just throw away, essentially, or scale away this final term here. And this dispersion limit does already have a very beautiful twistor theory that was constructed back in the 90s or early 2000s by primarily Nigel Hitchin, and then in much more detail by Maciek Janowski, Lionel Mason, and Paul Todd. So just to set the scene, what's going on is that instead of R3, we now consider a more general 3-manifold M, and we say this manifold is Weyl if it has a conformal equivalence class of metrics together with a torsion-free connection that isn't necessarily metric compatible in the usual sense, but the covariant derivative of this metric is proportional to the metric with some one form nu. And of course, if I rescale my metric using a Weyl transform, because I've only defined its conformal class, then this nu has some gauge freedom as well. If I rescale my metric using a Weyl transform, I'll pick up some derivative of the Weyl transform on the left-hand side, and that'll amount to shifting my one form on the right-hand side. Now, although this connection is torsion-free, the fact that it's not metric compatible means the Ricci tensor formed from this connection isn't necessarily symmetric. And we say that M is Einstein-Weyl, not just Weyl, but Einstein-Weyl, if in addition the symmetric part of the Ricci tensor is proportional to the metric. Now, there's lots of stories about these generic Einstein-Weyl manifolds in 3 dimensions. There are lots of interesting examples of them. Flat space, of course, is an example. Anti-de Sitter space and de Sitter space, of course, are examples, but there are many, many more examples. But for today, what we'll be interested in is Einstein-Weyl metrics of this form. So here we've just got the flat metric, and then I've deformed it by some function u on R3 in a particular direction. So just I've added on a dx minus squared component. And this metric and the associated one form here satisfy these Einstein-Weyl conditions if and only if this function that we've added on u obeys the dispersionless limit of the KP equation up here. Now, how does this connect to mini twistors? Well, Hitchin proved that every Einstein-Weyl manifold has a mini twistor space, which is very similar to the mini twistor space we met for R3, in the sense that they're both complex surfaces. So they've both got 2 complex dimensions. They're complex manifolds, first and foremost. They've got 2 complex dimensions, and they contain at least one rational curve whose normal bundle is O2. So in the flat space case, that was just the CP1 at the base of the fibration of thinking of mini twistor space as the tangent bundle to CP1 with more general curved manifolds, we have to impose this as a condition on the twistor space. Now, that's true for Hitchin's theorem applies to any old solution of the Einstein-Weil manifold, but for these special solutions that come from the DKP equation, the dispersionless KP equation, they're related to mini twistor spaces, curved mini twistor spaces, which are just deformations of the flat mini twistor space, our basic one that we met in the monopole case, with the additional property that these deformations have to preserve not quite the holomorphic two-form that we used in constructing the monopole theory, but this thing together with that's normalized by some sort of fourth order pole that some sort of factor that introduces a fourth order pole at a particular point on the Riemann sphere. Some arbitrary point on the Riemann sphere, but a fourth order pole. So since mini twistor space is too complex dimensional, this two-form defines a holomorphic symplectic form. This fourth order pole means that it's invariant under the scaling of the homogeneous coordinates of the mini twistor space. This is an honest two-form, although a meromorphic one. And so it defines a symplectic form away from the divisor. And therefore, inverting it in two complex dimensions, it gives us a sort of holomorphic Poisson bracket, which explicitly, in terms of the coordinates lambda and mu in twistor space, takes this form. The condition that to get a mini twistor space that corresponds to a solution to Einstein-Weil, that corresponds to a DKP solution of Einstein-Weil, that we need to preserve this particular combination, this symplectic form, when we deform the complex structure of twistor space, amounts to saying that we want these deformations to be Hamiltonian with respect to this Poisson bracket. Right? If we want to preserve this symplectic form by deforming the complex structure, we should deform it along a Hamiltonian vector field rather than just any old vector field. Okay. So for some Hamiltonian, which I'll suggestively call A bar, it's just some smooth 0-1 form on the mini twistor space, the deformations of the complex structure away from the sort of standard complex structure, some sort of covariant one, are by these Hamiltonian vector fields using this Poisson bracket that we've got. And provided this is an integrable deformation, then Hitchin and Donachsky, Mason, Todd prove that the mini twistor space you get, the curved mini twistor space you get, corresponds indeed to a solution of the DKP equation. So to set that up as in the framework that we've been talking about for Self-Juliang-Mills and for monopoles, again, the obvious thing to do is just to construct a mixed topological holomorphic theory living on this space upstairs, this S2 cross R3. So this is a theory that I'll call Poisson-Chern-Simons theory. It's now a Chern-Simons theory rather than a BF theory because the omega we're using, the pullback of this holomorphic symplectic form, is weightless. There's no need to have an extra field B to absorb any homogeneity scaling. This thing is already weightless. So we can write a sort of Chern-Simons interaction, a Chern-Simons Lagrangian, but where the interaction here uses exactly this Poisson bracket that we had. And again, just as for monopoles, if I work in a gauge where the vertical component of A pointing along the fibers of this five-dimensional space over mini twistor space, the complex twofold, if I work in a gauge where that component vanishes, then again, the field equations imply exactly the sort of Hitchin construction, that we have a Hamiltonian deformation of the complex structure of mini twistor space. However, this theory's now got two subtleties that we didn't meet before in the case of the BF theory. So we said that this symplectic form has got a fourth order pole in it. And so this omega, the capital omega that we've got in our action, now has a pole, has a fourth order pole. And for this to be well defined, in particular for the propagator to be well defined, we must impose suitable boundary conditions on our field as we approach this divisor where we're sitting on top of this pole. Also, although we had a holomorphic Poisson bracket, a canonical Poisson bracket on the mini twistor space itself, just the inverse of the symplectic form on mini twistor space, we have to lift that up to the spin bundle, lift it up to this five-dimensional space in order to write this action. And there's quite a bit of freedom in exactly how you lift these vector fields, this Poisson bracket, from mini twistor space up to the spin bundle. And these subtleties are going to be important in understanding how to reduce this theory to a theory on R3. In particular, we're expecting from known theories of what's already known about twistor space and DKP, that somehow when we reduce this action down to R3 by working in a different gauge, we're expecting that we'll get some sort of theory that's equivalent to the DKP equations on shell. But to really obtain that, we have to take care of these two subtleties. So we'll consider those subtleties in just a minute. But before we get there, to now go to full KP theory, not just the dispersionless limit that was already known in twistor space, the idea is simply to promote this Poisson bracket to a Moyal bracket, a non-commutative structure. And I should mention that ideas that this would also be relevant for the twistor description of the full KP equations had appeared previously by Ian Strawn. Okay, so to Moyal quantize a Poisson bracket, whenever you've got a Poisson bracket, the first thing you have to do is to choose a way of splitting this bivector, this Poisson bracket, essentially, into a pair of commuting vectors such that the anti-symmetrization is the bivector. So of course, there's some freedom in how you do this. For example, I could add any amount of d0 onto d1, and when I wedge them together, I'll still get the same Poisson bivector. So there's some freedom in how you do that, and you have to make a choice in order to Moyal quantize the bracket. Okay. So for any such choice, we can define a star product in the standard way. So I just take the exponential of this antisymmetric combination of my two derivatives, d0 and d1, and this notation is intended to mean that when I expand out this exponential as a power series, all the derivatives in this first slot here act on the first function f over there, whereas all the derivatives I get acting in the second slot act on the second function g. And then at the very end of the day, so then I'll get a sort of tensor product of two functions, and at the end of the day, I just multiply those two functions together, okay, and treat them as functions on the same space as opposed to a tensor product space. And if you expand this out in powers of some formal parameter q that I've introduced here, the leading term, of course, is just the standard product, the standard commutative product of f and g. The first order deformation to first order in q, you just get the Poisson bracket of f and g, but then there'll be an infinite series of higher order deformations in this Moyal star product. Okay, so in our case, in the case of the Poisson bracket we've got on mini twistor space, down on mini twistor space, the natural way to split this is just to take d0 to be the derivative along the P1 base of mini twistor space, and d1 to be the derivative along the fibers of mini twistor space. So this is the fibers of TP1. And if we do that, then we get a star product, which implies that the mini twistor space is no longer commutative, but its homogeneous coordinates obey the following starred anti-commutation rules, following mu Moyal bracket. Okay, so it turns out this theory is largely insensitive. I'll skip over the details of exactly why, but the theory is largely insensitive to the choice of how we're going to lift these two derivatives up to the spin bundle. And the choice that turns out to be useful for our purposes is the following. So we take d0 to just be the standard lift of the same vector field that we had downstairs. So this is still exactly this thing. We just lift it up to twistor space, and we now view it as acting. So we lift it up to the spin bundle. This is the space with coordinates x on R3 as well as lambda. And I view it as acting at a constant point on R3 now. Whereas d1, the d mu derivative, mu was some combination of coordinates pointing along the R3, and it's convenient to lift that vector field so that it looks like this. And sometimes I'll, for shorthand, call this derivative d by dx plus. Okay, you can check that this particular, the bivector you get from this lift, so this lifted bivector, does indeed invert the pullback of the symplectic form on the mini twistor space, pulled back to the spin bundle PS, and that the corresponding Poisson bracket does indeed obey the Jacobi identity. So this is a valid lift of these vector fields. And if we use this star product that we get on the spin bundle PS, using these two vector fields, then you find that the x's, the coordinates on R3, commute among themselves in the usual way. So R3 remains perfectly commutative. We're not making any sort of non-commutative space-time. However, the coordinates on R3, these x's, again, alpha, beta, remember, are symmetric 2 by 2 matrix. So these are just coordinates on R3. it no longer commutes with the spectral parameter. It no longer commutes with these coordinates lambda on the CP1. So there's some failure of commutativity there. Okay, so we're not going to be dealing with a theory that's non-commutative on space-time or on R3, and we shouldn't be because KP, of course, lives on perfectly ordinary R3. But somehow the space will fail to commute with the spectral parameter in this theory.
So I have one question.
Yeah.
So usually we introduce non-commutativity into space-time coordinates. And then in gauge theory, this corresponds to the background B field. But is there any physical meaning of this non-commutative parameter in this?
Yes, it's exactly what you said, but we'll get there. Well, we'll get there soon. We'll get there soon. But yes, it is exactly going to be related to a background B field, or at least that's
Really?
one way.
Oh, really? Okay, okay. Thank you very
Yeah.
much.
So here I've just my logic so far has just been that we know that the Poisson theory is related to the dispersionless limit, and it's very natural once you've got a Poisson Chern-Simons theory to promote that to a non-commutative Chern-Simons theory. And I'd like to explain why that gives us the full KP equation, including the dispersion term. The physics of where this comes from, or how you might construct such a theory, we'll go into in a few minutes' time. But yes, your question's exactly right.
Okay, okay. Thank you.
Okay, so to build our non-commutative Chern-Simons theory, we don't just need a star product, we need a kinetic operator as well. We need a kinetic term in the Chern-Simons theory. And so the star product that we use had better be compatible with this kinetic operator. Now, what do I mean by compatible? Well, what's going to be important is that this kinetic operator should distribute over the star product. However, if we look at the kinetic operator we actually had in our Poisson theory, that's this d twiddle, which remember was the de Rham operator along the fibers of the spin bundle over mini twistor space together with the d bar operator on mini twistor space. So this kinetic operator that we had before fails to distribute over the star product. If I compute d twiddle of the star of two functions or of two forms, you find the first two things are exactly what you'd like. They obey a sort of Leibniz rule, but then there's a sort of failure of the Leibniz rule that knows about q squared. So it's of order q squared. You wouldn't see it in the Poisson theory, but you do see it in the non-commutative theory. And this failure of d twiddle to distribute over the star product means that if you wrote down the obvious non-commutative Chern-Simons theory using this d twiddle operator in the star product, you'd find it just wasn't gauge invariant. The action just wasn't gauge invariant, even in the Chern-Simons sense. Now, fortunately, miraculously somehow, we found that this could be remedied by modifying the kinetic operator. So we have some understanding of why this works, but not. I think there's probably something deeper as to why this had to work that we perhaps haven't got to. Anyway, so we find that if we modify this d twiddle operator by adding on a higher order derivative piece, then this new capital D twiddle operator does distribute correctly over the star product. So it does obey exactly these relations that we want. It obeys the nice Leibniz rule. And together that means that this space of forms, 0-1 forms on the mini twistor space together with real forms along the fibers, the star product and this derivative operator form a differential graded algebra. It's quite surprising, you might think, that this holds. After all, we've got this third order derivative in x here. So naively, you wouldn't expect this operator to obey a Leibniz rule because of this third order derivative. But somehow this failure of the naive operator of this operator to obey a Leibniz rule is compensated by the higher derivatives that are appearing in the star product. So that altogether, it does obey a Leibniz rule over the star product. It's quite striking that happens. Okay, so with these ingredients, we can now define our non-commutative Chern-Simons theory on this real 5-manifold PS. And it's just the obvious thing. So it just looks like an abelian but non-commutative theory living on this 5-dimensional manifold. And again, it's going to be mixed topological and holomorphic because we've pulled back all the holomorphic forms from mini twistor space. So what's left is either a real form or an anti-holomorphic form. And on shell, this will describe an integrable but non-commutative deformation of the complex structure of mini-twistor space. And in the limit that Q goes to 0, of course, since these A's are all wedged together as well as being multiplied by the star product, the leading term at Q goes to 0 vanishes by the wedge product, and the sub-leading term just recovers that interaction. Okay, so I mentioned before that we've got a pole, we've got this fourth order pole in the measure omega. If I use a local coordinate z that such that this pole is at z equals naught, then we have to impose some boundary conditions on these fields to make sure that that pole is harmless. And the boundary conditions that turn out to do the job are these. So we want the z bar, that's the CP1 component of this gauge field, to be order z squared near z equals 0, near this point. And then, whereas we need this other combination of the remaining two components to also be order z squared. And because we restricted the behavior of the gauge field itself near this divisor, near z equals naught, that also means that we have to restrict the type of gauge transformations we're allowed. They have to be compatible with this boundary condition. Okay, so now let's show that this non-commutative Chern-Simons theory is equivalent, does reduce to KP theory on R3, and I'll say exactly what I mean by KP theory. Okay, so as always, just as we saw right at the beginning of the talk, we do this by just Kaluza-Klein expanding on the CP1, thinking of our 5 manifold as just CP1 cross R3, we Kaluza-Klein expand on the CP1, and because I'm free to imagine that I've picked a metric that the size of the CP1 has shrunk to 0, everything apart from the 0 modes in this KK mode, in this KK expansion, are going to disappear. They're all going to be BRST trivial. Okay, so I mean, in a gauge in which the metric has shrunk to 0 size on the CP1, they will decouple. In any other gauge, they'll be BRST trivial. They'll be a gauge equivalent to 0. Now, to do this reduction in a little bit more detail, what we have to say is we have to find the gauge invariant information in the components of A along these CP1 fibers, because that we cannot remove by any sort of gauge freedom. And it turns out that this gauge invariant information is captured by a sort of derivative of the holomorphic frame. I apologize, there's an equal sign missing here. So this is defining phi of x. So what are the ingredients on the left-hand side? Well, it's a holomorphic frame U on the fiber CP1 above some point X in R3. So I pick a point in R3 and I look at the CP1 above that point, and I define a holomorphic frame on that CP1 fiber in the sort of obvious way. So it's covariantly propagated along the CP1 direction using this covariant derivative operator. I could use the capital D here, but it turns out the difference doesn't matter on CP1. So this is like a holomorphic analog of a Wilson line. It obeys some sort of covariant propagation along this holomorphic direction, and it's normalized so that when these two endpoints are both the same, it's equal to 1. So the space-time field phi of x is going to be, with this equal sign, it's going to be the derivative of this holomorphic frame in the holomorphic directions along CP1, and then evaluated in a limit when these two endpoints become the same. Of course, if I just took this limit before differentiating, I would get nothing. This would just become 1 and then die under the derivative. But if I first differentiate and then take the limit, I get something interesting, which no longer knows about the sorry. I've said this badly. This should be the limit as z goes to naught. This should be u of z comma naught, naught being where the pole was in my on my CP1, and I should be taking the limit as z goes to naught. So I take u of z to 0. So it's sort of coming back to this point where the pole was on the CP1. I differentiate it, and then I take the limit as z goes to 0. Apologies that I've got that wrong. Okay. But we get a different holomorphic frame for each point x in R3, and so what comes out of this still knows about x. If you like, it still knows about which CP1 we're talking about. Okay, so that's the gauge invariant information on the components of A along the fiber. what we have to do now is relate that to the remaining components of A. And we do that just using some partial equations of motion of the non-commutative Chern-Simons. So these are the mixed components of the equation of motion that point along the CP1 direction, which now involves this gauge invariant information here, and along the R3 direction. So one of this two form here, one of its indices is anti-holomorphic along the CP1, and one of its indices is going to be anti-holomorphic in R3. And these forms just ensure that we're extracting the right combination of components here. Okay. So this relates the remaining components of A to this gauge invariant information. And so essentially all the components of A can now be thought of as being determined by this space-time field phi of x. So when you go through the details of that and you integrate out the CP1 fibers, what comes out is this action. The structure of this action is interesting. We'll talk about it in a minute. But first, what I'd like to explain is that if we find the equation of motion for this action, it isn't quite the Kp equation, but it implies the Kp equation if you take a further derivative of the equation of motion. So the equation of motion for this thing gives me some equation of motion for phi, which involves up to fourth order derivatives of phi. That equation isn't the Kp equation, but if I differentiate the whole equation through by d plus, then and I relabel my field as d plus of phi as u, then I'll find that I do get the Kp equation for u. Okay, so the Kp equations themselves are not the Euler-Lagrange equations of any action, but phi is like a potential for the Kp equation. Where have these terms in the action come from? Well, the standard kinetic term has come from the standard kinetic term of our Chern-Simons theory. Once you chase through exactly how the various field components are related to each other, this dispersive term, which has got an extra, so there's two derivatives here. There's an extra two derivatives. There's two derivatives here. There's four derivatives there. The extra derivatives here have come from this modification of the kinetic term in the Chern-Simons kinetic term. So the original Chern-Simons kinetic term, of course, just had just a single derivative, and so we sort of gain an extra derivative on doing the reduction in the standard part of the action. But our modification of the Chern-Simons kinetic term, that had these third order derivatives, so it's got two derivatives more than the standard derivative. And that leads to this dispersion term, which has got two derivatives more than the standard kinetic term. But it's still quadratic in phi, so it's still coming from the kinetic term of the Chern-Simons. The non-commutative vertex of the Chern-Simons, of course, gives me this cubic term in the field. Again, the fact that the field turns into these derivatives of phi is something you have to chase through the reduction. And it's quite striking that all the effects of the star product somehow go away in the reduction. It's because they all, technically it's because they all involve the same spinner, and by the time you contract up all the spinners, none of the higher terms can contribute. But in any case, the only effect of the star product in this reduction is to provide us with the right kinetic operator. It's also worth saying that to get to this action, what we did was we figured out we figured out what we could gauge, what the gauge invariant information in A was. So this was essentially fixing a gauge, saying that the gauge invariant information in our gauge is going to be this field phi. That's the components of A along the P1. And then I used the mixed P1 R3 component of the equation of motion to relate this information to the remaining components of the field on twistor space. But the field equation of this action is also the field equation of the remaining field equation, which is the R3 components of the field equation in the mini twistor action. And so this equation of motion comes from the sort of remaining zero curvature equations of the field in the Chern-Simons theory. And so this field really, sorry, I don't know why I put a prime. I think that's left over from an old transparency. This zero curvature on the remaining components of A is really showing that the field A in twistor space or on the spin bundle is playing the role of a lax operator for the Kp equation. And the fact that the lax operator is embedded in the zero curve is embedded in the twistor gauge field is a standard thing in twistor theories. In fact, it was true, for example, for our self-Joule-Yang-Mills and for our monopole theories as well.
Sorry, I have one question. I'm sorry.
Please.
You said higher order derivative vanish. It's quite surprising. So is it expected?
Let's see. So I don't know whether it was expected or not. We were pleased. So what happens is that all those higher order derivatives come contracted into the same spinner. So the star product, the Poisson bracket started. Remember, the star product meant there was non-commutativity between the spectral parameter and the space-time coordinates x. And so some of the derivatives in the star product will differentiate along the CP1. Others will differentiate along R3, but always in the same direction in R3, specified by the same spinner. It's that same spinner. It's always, sorry, I've rather hidden it in my notation here, but it's always this spinner that I've called iota that's appearing in the star product, that's appearing in derivatives in the star product, where this iota started out life as the place where my measure had poles. Okay, that's where the iota entered. Now, because these derivatives are always pointing in this iota direction, and iota is it's always the same spinner. When you integrate over the CP1, all those iotas contract with each other, and you just get 0. So all the higher order terms in the star product go away. I should say that that's really special to the way we've chosen to lift this bivector from mini twistor space up to the spin bundle. We found actually that there's another choice which is equally good, a different choice of how you lift, where you get a slightly different star product. With this different star product, the original derivative, it does distribute, so you don't get this extra term. There's no need to modify this dispersion term. If you chase through, so if you write down with the different star product, the non-commutative Chern-Simons theory with the original derivative, and chase through what you get on R3 with that, you find that you don't immediately get this dispersion term. So this term is absent, but now you do get an infinite series of cubic interactions with higher and higher derivatives. So now with that different lift of the star product, the star product does descend to give you something non-trivial on space-time. And there's then a field redefinition that relates the two actions to each other. So again, they're equivalent by a field redefinition. So yeah, I could have presented it that way, and perhaps I should have done. But
okay, okay, thank you very much. Yeah, still complicated to me, but yeah, it's okay. Please go. Yeah.
Okay, so what do we gain from thinking of the theory this way? Well, in both the Costello, Witten, Yamazaki, and twistor philosophies, the theories are integral because they've come from a mixed topological holomorphic theory. It's the fact that they descended from these theories that made them integral down on R3 or space-time, whatever it was. Now, as a consequence, since these theories are integral, they have some sort of infinite dimensional symmetry, and in quantum field theory, the Coleman-Mandula theorem will then tell us that their perturbative S matrix should vanish. All the scattering amplitudes, the perturbative scattering amplitudes, should vanish in these theories. That's easy to see how it comes out of this story, because, for example, a momentum eigenstate on R3 or on our space-time with some momentum that looks like this is represented by a non-commutative Chern-Simons state, a state in the non-commutative Chern-Simons theory that's localized at a point on CP1 where this point is specified by what the momentum of our momentum eigenstate was. Now, to reduce to space-time, we chose to work in a gauge where the volume of this CP1 was arbitrarily small. That just kept the zero mode to the KK expansion. But since it's just a gauge fixing, we're free to take the opposite limit. We're free to choose a metric that instead makes the volume of this CP1 arbitrarily large. And in that limit, since all these momentum eigenstates are localized at different points on the CP1, as I make the CP1 arbitrarily large, all of those states become arbitrarily far apart. And if you go through the power counting argument, you'll find that they just can't interact with each other. The propagators are infinitely suppressed in this limit. So since they don't interact, it's trivial then that all the tree amplitudes of these theories vanish. So for example, it's not trivial that the tree amplitudes you would write down from this theory, you've got a cubic interaction, you've got some complicated propagator. It's not immediate to see that all the tree amplitudes of this theory vanish if you're a quantum field theorist. If you're an integral systems expert, you would say, well, they have to because it's integrable. But if you don't know that this is integral, it's not obvious that those tree amplitudes will vanish. Certainly, there are lots of Feynman diagrams you can draw at tree level. But in fact, this argument proves that they have to, and we've verified directly as a way of checking that we have got the right theory, we've verified directly that they indeed do vanish. Now, that was a tree level argument. At the quantum level, since these mixed topological holomorphic theories are chiral, they involve d-bar operator, not the full de Rham operator, gauge invariance may be obstructed. There may be some gauge anomalies. And so our argument that the theory we get on space-time by taking the volume of P1 to 0 and is integrable, which we saw by taking the volume of P1 to be arbitrarily large, that argument might not be valid anymore because we had to do various different gauges to see the equivalence of those things, and gauge transformations may simply not be valid at the quantum level. I mean, these theories might not just simply don't exist at the quantum level if they've got a gauge anomaly. Now, in the theory we started with, the BF theory corresponding to self-dual Yang-Mills, indeed that suffers from a one-loop anomaly. That chiral theory does have a one-loop anomaly in twistor space, which, thinking of twistor space as six-dimensional, is just a box diagram. It was first computed by Costard and Paquet. And consequently, classical integrability of self-dual Yang-Mills breaks down in the quantum theory. And indeed, this has sort of been well known for many years because integrability would imply that there are no scattering amplitudes, but self-dual Yang-Mills does have a whole family of one-loop scattering amplitudes. They've been computed. Right? And the fact that these one-loop amplitudes were indicating that the theory had to fail to be integral at the quantum level was first pointed out by Bardeen, although the sharp reason, I think, was given by Costard and Paquet. Similarly, the purely holomorphic Poisson-Chern-Simons theory, if we did it for Penrose's nonlinear graviton, we get a Poisson-Chern-Simons theory living in 6 dimensions rather than the 5-dimensional version I've been talking about today. That 6-dimensional theory also has a one-loop anomaly. And so Penrose's nonlinear graviton fails. It does not correspond to something on twistor space, at least for pure self-dual gravity in the quantum theory. However, in today's theories, relevant for either monopoles or for KP, since the space-time they lived on was a 5 real dimensional space, there are no one-loop anomalies in odd dimensions. And so this KP theory and also the monopole theory should still preserve their integrability, even if we view them as theories at one loop. Okay, so to test that, we wanted to compute the simplest 4-particle one-loop scattering amplitudes in this theory, just treating this as an action and drawing some Feynman diagrams. And at one loop, the 4-particle scattering amplitude receives contributions from the following sets of diagrams summed over various different channels. We've computed all these, but we're still checking. I mean, because of these very high orders of derivatives in the interactions, it turns out it's a little bit difficult to compare them and sum them up. So we're still in the process of checking that these things do indeed cancel. But the expectation is they should, because this theory should still be integrable at the quantum level, at least at one loop. But assuming that these diagrams for the 4-particle one-loop amplitude vanish, then we have got an argument that proves that all the n-particle one-loop amplitudes also vanish. So the complete, as long as this 4-particle amplitude turns out to be 0, all one-loop scattering diagrams should be 0 in this theory. Essentially, because if they weren't 0, you could cut them and find a tree-level diagram on one side of the cut. But we already know that all the tree diagrams are 0. Now, even more optimistically, we might hope that this non-commutative Chern-Simons theory exists not just to one loop, but to all orders in perturbation theory. And some reason for this optimism is that this is certainly known to be true for a very closely related theory. Here's a non-commutative Chern-Simons theory, but not on R3 cross P1, but instead on R3 cross C or C2 cross R. Okay, so we worked on R3 cross CP1 with a complex structure on a C2 inside R3 lifted from the mini twistor space. But if you just work on C2 cross R and write down essentially the same theory, then that theory is known to exist to all orders in perturbation theory as a quantum theory. The difference for us is because we had a meromorphic two-form rather than a holomorphic two-form, we had to impose some boundary conditions on A, but otherwise it's very, very similar. Now, getting close to what Masashi was asking, this theory is interesting. It's very, very closely related to topological strings, the topological strings of my title. So this theory is known to arise in various ways. It's the open string field theory. It's the target space of a mixed A-B model on C3. So you put the A model on C2, the B model on C2 and the A model on C, and the A model reduces just down with branes just reduces to a Lagrangian, this R inside the remaining copy of C. Alternatively, it's the closed string A model on C3 with a background B field to provide this non-commutativity. So that's exactly what Masashi was asking about. And also it appears as a twist of M theory in an omega background. So this theory has lots and lots of connections to topological strings and to twisted M theory, all of which are certainly very interesting. And we're hoping that they do carry on to the theory that we've got, which is closely related and describes KP. Now, one reason that's, I think, particularly interesting is that, of course, Chern-Simons theories would describe the fundamental strings, the fundamental topological strings, but non-perturbatively, those topological string theories would also contain various branes. In particular, if we view it as coming from twisted M theory, then there are M2 branes and M5 branes. The M2 branes will wrap a real line inside our fivefold. The M5 branes wrap a holomorphic curve inside the fivefold PS. Oh, that's what I said. And living on these branes is their own theory living on these defects. And in particular, these M5 support a theory of chiral fermions. And you can get a sort of type of, not ADS CFT, but some sort of holographic duality between the non-commutative Chern-Simons theory in the bulk and this theory of chiral fermions living on two dimensions, wrapping on this holomorphic curve. These chiral fermions, if we integrate them out, what you'd get is some sort of determinant of the kinetic operator of the chiral fermions living on this curve. So this is the determinant of this covariant star product deformed kinetic operator restricted to the curve where these chiral fermions lived. Okay. And it's natural in our context to imagine that this determinant of the d-bar operator is essentially the tau function. I mean, it's Sator's famous tau function. The fact that it appears this way in twistor spaces, in topological strings in particular, is due to a Ganigich digraph from Waffer and collaborators. It's also been seen in twistor space context before as well as in the DKP context. But here we should expect it's to do with the determinant of this non-commutative d-bar operator. Now, what are these d-branes? What are these M2s and M5s? Well, they're solitons in the topological theory. And so they should correspond to solitons in KP by our correspondence. But solitons in KP are, of course, just branes. These branes are just waves approaching the beach. And so the idea would be that these non-commutative instantons on our spin bundle, which should indeed reduce from, there should be symmetry reductions of non-commutative instantons in twistor space for Self-Juliang-Mills, but reduced in a particular way and where the non-commutativity isn't entirely in space-time, but rather is between space-time and the CP1 directions. Very much as for example, Masashi has studied. Those sorts of branes in this context should just be waves. So often people say that there's no observable consequences of string theory, and it's completely impossible to observe anything. But here you go. These are d-branes in topological string. They're just waves on the beach. And of course, the scattering of these non-perturbative solitons can indeed be non-trivial. And here's some beautiful examples of such solitons. Okay, how much time do I have? Well, I could carry on, but this might also be a good place to stop. So it's sort of up to you.
No problem, no problem. Please
I should carry
continue.
on. Okay. Well, let me just say a few things about an infinite dimensional chiral algebra. Okay. So something else we get out of this construction in the Chern-Simons theory is that we can explicitly construct an infinite set of non-local conserved charges that the KP theory has. I mean, of course, it's well known that it will have such an infinite set of charges, but usually, in terms of the field of the KP equation itself, it's quite complicated to write those down explicitly, right? Especially by the time you get to the higher charges. However, in the non-commutative Chern-Simons theory, these charges all come from something called a universal surface operator. That takes this form. And it's essentially so the case. Okay, the simplest example of this when I don't have any derivatives. So when s is 1 here, if I just keep the s equals 1 term, this would exactly be a holomorphic frame along the CP1. This would exactly be the solution to that covariantly constant frame that I called U on the CP1. But now I've got some higher derivatives where these derivatives are acting in normal directions to the CP1. And the reason we're allowed those in this mixed so normally if you had a gauge theory, you're familiar that you'd have Wilson lines as being the natural observables in the gauge theory. You can believe that in a holomorphic theory, you have some sort of holomorphic analog of the Wilson line where they're defined using the d-bar operator along a complex curve rather than the standard de Rham operator along a real curve. But in a holomorphic theory, you have further operators which involve holomorphic derivatives of the gauge field. And the reason you get these is that in a holomorphic theory, these holomorphic derivatives are not related via the action. They don't appear in the action. So if you tried to write this down in a real Chern-Simons theory, you'd find that using Schwinger-Dyson equations, they were related to other operators, other Wilson lines that you'd already written down. But holomorphically, in a holomorphic theory, they're not. They're independent. And so these are new operators we can get. And in our non-commutative theory, this exponential is understood as its power series, as a formal power series, and that power series involves the star product, of course. Now, I've snuck in here some weird symbol Vs, and you can just think of that as a particular coupling, a choice of coupling that I make for my gauge field onto this line. But this choice of coupling is constrained in various ways. First of all, it must transform in the right way so that this thing can be properly integrated over CP1, so it must balance any weights I've introduced in A, it must be a form of appropriate degree. All of that just says it's a chiral primary of weight S. But much more interesting is that it must transform so that this whole operator behaves nicely under gauge transformations. Okay? So the chiral algebra is going to come from requiring that this operator is invariant under gauge transformations, which for our non-commutative theory with its modified derivative operator looks like this. So at tree level, there's cancellation between the following sets of diagrams. And just as for standard Wilson lines, this first diagram represents the nonlinear transformation. So this A and C, these two incoming lines represent the A and C interacting with the Wilson line. Whereas the second diagram represents the abelian part of the transformation, but acting on the next order in the expansion of this Wilson line. So diagrammatically, the reason a normal Wilson line is when you expand out the path-ordered exponential, the reason the normal Wilson line is gauge invariant, if you do it in this sort of slightly clunky diagrammatic form, is that there's a compensation between the non-abelian transformation of some term lower in the power series with the abelian transformation of some term higher up in the power series of the exponential. And diagrammatically, that's just what this is saying. Now, we've put all of these arbitrary coefficients in front of our couplings to A. So if I tell you what my gauge transformations of A are, then the behavior of this is going to be defined, and my gauge transformations of A are determined by the bulk theory. And you'll find that these diagrams cancel, provided these objects Vs have OPs, so they behave like a little quantum field theory living on this CP1, and the OPs have to define W1 plus infinity. Okay, some sort of non-commutative deformation of of little w1 plus infinity, which would be the algebra we'd obtain in the Poisson case, which is the algebra of area-preserving diffeomorphisms. And the area here, of course, is the area of mini-twistor space as measured by this holomorphic symplectic form. So we get a non-commutative deformation of this algebra, which is capital W1 plus infinity, coming from these universal defect operators. Now, again, that story is reasonably well known. The fact that you should get this capital W1 plus infinity algebra coming from KP has certainly been said before. But we can now start to consider quantum corrections to this. So at one loop, we get further corrections from the following one loop diagrams interacting. So my vertical line here, I should have said this before, my vertical line represents that universal defect operator, that sort of generalized Wilson line. And these diagrams are the gauge fields coming in and interacting with this Wilson line. And at one loop, we can get these diagrams. And okay, so we're busy trying to compute these things, at least in the Poisson-Chern-Simons theory, the simpler case. We've computed these first two diagrams and they cancel. But this final diagram is a little harder to compute, and we think it doesn't cancel. It isn't zero by itself. And so these remaining diagrams will give us a further deformation. If we're in the Poisson-Chern-Simons theory, it'll be a further deformation of little w1 plus infinity. If we're in the non-commutative Chern-Simons theory, it'll be a further deformation of capital W1 plus infinity by some new parameter. So to go from little w1 plus infinity to capital W1 plus infinity, we had to turn on the non-commutative parameter Q. But now we're turning on a further new parameter, which is like h bar, the loop deformation parameter from the QFT point of view. And the only candidate for what this could be isn't a Lie algebra. This capital W1 plus infinity doesn't admit any deformations as a Lie algebra, but it does admit deformations as a vertex operator algebra, which is sometimes called curly capital W1 plus infinity. Okay. And this two-parameter family of deformations by both non-commutativity and h bar are believed to be the most general deformations of this algebra of area-preserving diffeomorphism. Okay, I think I really will stop there. So I was going to mention some connections to celestial holography, which is sort of another one of my interests. There's another way of seeing this algebra from scattering processes, or form factor processes, I should say, in space-time, but perhaps I'll skip over the details of that. But this is just another way that from the theory in space-time, the theory of this scalar field phi, you can recover the same algebra by considering perturbative processes in the presence of some defect in that theory as well. And you get the same W1 plus infinity algebra at the classical level. Okay, so my conclusions. So we've seen that the KP equations are equivalent to the equations of motion of non-commutative Chern-Simons theory on this 5-dimensional manifold PS, which is just S2 cross R3. And so for me, I'm very pleased because the KP equations are now incorporated into this general scheme of mixed topological holomorphic theories in twistor space, the idea that all integrable systems should arise from some sort of mixed topological holomorphic field theory that lives on some space incorporating the spectral parameter, and in particular lives on twistor space. To go between the dispersionless limit of the KP equation to the full KP equation corresponded to making the mini-twistor space non-commutative, not just having a Poisson structure, but having a star product. And the universal surface operators that we could point, these generalized Wilson lines, supported a chiral algebra, which at the classical level you identify as capital 1 plus infinity, and the quantum level will be a further deformation of that. I should say that what we've done is really just the first example of a much broader class of systems. So, for example, many other integrable systems such as these fit into the same framework. For example, the non-commutative Chern-Simons theory I wrote down was essentially abelian. There was the gauge group was C star, although it was non-commutative. If you make the gauge group GL2, sorry, it might be SL2. If you make the gauge group SL2C, you get the Davies-Stewartson thing. So if you do non-commutative SL2C Chern-Simons theory, you get the Davies-Stewartson integral system. We're still exploring exactly what happens when you quantize this system. Okay, I'm a quantum field theorist, so I like to do that. Maybe it's less relevant for waves at the beach. And there are important connections to topological strings, twisted M theory, and twisted holography. And I think the story, the slogan that I like most about this is that the solitons of the non-commutative Chern-Simons theory, these are these M5 branes or various other D branes, they really are just thought of as solitonic shallow water waves. to really set up some explicit examples of that and really recover, for example, the tau function of one of these solutions coming from a D-brane in the non-commutative Chern-Simons theory is something we're working hard to do right now. So I shall stop there. Thank you very much.
Okay, thank you very much for fantastic talks.